Okay, so we've talked a lot thus far about how to generate Bode plots manually. And obviously that's useful, but it's useful more for kind of thinking about specifications. So if you look at your current homework, say problems 5 and 6, that's where that kind of becomes useful. So think generally about specifications. Very often we want to generate the actual true Bode plot, which doesn't look exactly like the approximations. So when we first introduced Bode plots, we took an example of an RC circuit, and in particular it was an RC low-pass filter. And what we had is h of s equals 1 over 0.001 s plus 1. So what we see here is that the magnitude of this guy is constant out to 10 to the third, right? Radians per second. That makes sense because our break point is 1,000 radians per second. And then we see the straight line approximation kind of dropping down. The actual response actually dips down a little bit below that. The maximum difference here works out to be about 3 decibels. It's not huge, but there is a little bit of a difference. The question becomes, well, how do I make the actual response? Well, one way you could make the actual response would be to say, well, you know that the magnitude of h of j omega is equal to 1 over the magnitude of the bottom. So in this case, the magnitude of the bottom would be 1 plus 0.001 omega squared. So you could do that, and you could plug in omega equals to a particular vector of values, and then go into MATLAB and plot omega versus whatever you called this guy. So I don't know, let's call it h mag. Okay, I could do something like that, but MATLAB has an approach to be able to do it using the command called Bode. All right, so let's take a look at an example. Let's say I took this particular circuit, and I'll use the same values here. So whatever RC values I had for the low-pass filter here, I'm going to use the same ones. So let's call this guy R. Let's call this guy C. If I say here's V in on this side, here's V out on this side, you should be able to see that I do a voltage divider to say V out of S equals V in of S times R over R plus 1 over SC. And by now, you should be able to see that that means we have an h of s equal to V out over V in equal to SCR over SCR plus 1. You should be pretty confident at seeing that. And let's say our RC value is 0.001. So that gives us an h of s equal to 0.001 s over 0.001 s plus 1. And let's say I want to get the exact Bode plot of that particular function. Well, to do that, we write code like we have right here. Okay? So I took that transfer function, 0.001 s over 0.001 s plus 1. And I look at that and I see I've got, it just in the context of remembering that these transfer functions are always rational functions of s, meaning that there's a polynomial of s on top and a polynomial of s on the bottom. If I look at this in sort of a more general context, I see that the squared term doesn't exist on the top. The first order term does. The constant term does not. Whereas on the bottom, the second order term doesn't exist, the first order term does, and the constant term does. So the way we enter this into MATLAB is I create a numerator and denominator vector, okay? And the highest order term that I have always goes first. So in this case, I have an A1 term, so I put it here, 0.001. And I don't have an A0 term, in other words, it's equal to 0, so I have to set that to 0. On the denominator side, I have a B1 term and a B0 term, so I enter both of those. Okay, basically what it's saying is I always have to have the first entry in this vector. All right, the first entry has to be the highest order term that I actually have. So if I had, as an example, let's say h of s equal to 1 over s squared plus 2s plus 3, in that case I would say my denominator, I start with my highest order term, that's the s squared term, so it's 1, then 2, then 3. okay? And for my numerator in that case, it would be 1, right? My highest order term is the constant term, okay? So I don't have to do this, but I often do. I write h equals tf, meaning transfer function of num comma den, and then I can run the Bode command. Now you can run Bode two different ways. I can say Bode num den, that works fine, or I can say Bode of h, which is the transfer function that I got. If I do that, I get this output. So on the top I have the magnitude plot, right, which is always shown in decibels by default. But it also shows me the phase plot. Now, we haven't talked about how to make approximations to the phase plot. You can. It's a little bit more complicated and generally not as useful, and so we didn't talk as much about it. But I should be able to make some sense of this, at least, if I look at it, right? So it starts at 90 degrees at low frequency, and it ends at 0 degrees once I get to a high frequency. And that should make sense if you think about the nature of my transfer function as 0.001 s over 0.001 s plus 1. At low frequencies, this term here doesn't matter too much, but this one certainly does. And the angle of this guy would be 90 degrees. If I looked at a pole would eventually give me negative 90 degrees, and their combined angle would be 90 minus 90, or 0. All right, we're not going to talk a whole lot about that, but if you look at this carefully, you should be able to make some sense of it. All right, this becomes particularly useful to make these sorts of diagrams like this once we get into more complicated problems. Like, so for instance, once we give you problems where you have complex conjugate poles, okay? We haven't talked at all about how to deal with complex poles. If you think about every problem we've given you, the poles that we've given you, the poles and zeros are always real, but that doesn't always happen. All right, and so you guys will deal with some of those in the homework, but we ask for you to deal with it through MATLAB.